Hi guys, in this tutorial I'll demonstrate how to now determine the true tension T in the ropes, given that now part or some of the pulleys here actually do have friction. Now what you have to get in mind is that in the previous calculation what we determined was the value of T here that is needed to support our beam here in equilibrium. Now it happened that since there was no tension throughout these pulleys, there was no friction, throughout the pulleys. It implied that the tension T here would be the same as the tension that the cars would have to pull in order to sustain this position. But what if some of the pulleys here do have friction? Well, one thing doesn't change. You still need that force here to maintain equilibrium. So that force will still be needed. So the value we calculated earlier on is what is going to be present from this end up to this end. Now, the only section where things are changing is this part. So now we're going to draw a free body diagram, or we're going to now analyze this section separately to determine what is happening there. Well, if we start by just going through the question, you observe that the question says that the bearings in the pulleys D and F, so that means this is D and this is F, these were deformed badly, thus causing jamming. So when the two belts, the two pulleys were jammed, what this means is that the pulleys, these two pulleys stopped rotating, implying that now they will develop some form of friction as the rope passes there. What does friction do? It now changes what the tension here T will have to be. What we need still doesn't change to maintain equilibrium, but what needs to be supplied now will be more. Why? Part will have to deal with that friction that has now just developed. Now, how do we do this part? Well, I'm going to draw these pulleys separately so that we analyze what is happening. But the question does specify that the pulley E remains functional even though it only rotates clockwise. So we're going to focus on the pulleys D and F, assuming that the tension being supplied by the vehicles here is greater than what is happening in those pulleys. So let's pick the pulley D, for example. So if you pick the pulley D here, what do we see? Well, we observe that first we have the tension going this side, going towards that's E. We have the tension going first towards E in that direction. And then we have the tension going towards point B. So that is going to be the tension going in this direction. Well, the tension that has to go this side towards B, it has to be enough to maintain equilibrium. And we calculated in the previous calculation that we did determine that to sustain equilibrium for that beam, this is how much we need. So it doesn't change the fact that the one that should go this side, since the question does say we are to maintain that equilibrium position still, it implies that this still has to be what is going this side. So at least we know the tension that is going here. Or this is from, let's say that's from D to B. Okay, now next up we have the tension that is this side. I'll label this as, let's say T, I can say B to E, D to E. In this case, to determine what we're going to do, it's like we're going to work this backwards since we know what we need here. So we're going to use what we know to determine the tension here. Now the tension here, because this is still free to rotate, will be the same as the tension here. In the tension here, now we're going to use this pulley here to determine the tension finally that we need that side, which is the true tension. Now, how do we do that? Let's start with this one here. For this case, we know to say that if we wanted to determine the tension that side, the formula here would have to be, so we're going to use T2 is equals to T1, and then we have E, and then here we're going to have the coefficient of friction, and then we have beta there. Beta here is just the coefficient of static, sorry, not that, that's the coefficient of static friction. Beta here is just the angle of belt to surface contact measured in radians. So you have to remember that this angle has to be in radians. Now, what you have to understand here is the relationship here between T2 and T1. So how do you determine which one is going to take the position of T2 and T1? Well, all you have to see here is that T2 must be greater than T1 in this case, if of course any form of equilibrium is going to be achieved. Why is it supposed to be so? Well, the belt here, or should I say the pulley here, has friction. the pulley is going to reduce whatever is passing here. So what we're supplying it must be greater than what is coming out the other side. So here we see that TDE has to be greater than TDB. In other words, TDE, I mean, is the one that is taking the position of T2, and TDB is the one that will take the position of T1 in that formula. So in other words, we're going to have, in this case, we're going to have TDE being equal to TDB, and then we have E to the mu, and then we have the beta there. So already, remember that we already know what this one here is, TDB, this one, TDB. We already know what this one is. So all we have to do is substitute it there. That's 920, is the decimal place there? Yeah, 920.675. Okay. So we have, this becomes 920.675 E. Now we need to know what the coefficient and what that angle of contact is. For this case, let's see what is our mu. So that's pulley D. So for the pulley at D, let's see, mu between the wedge. So mu between the rope and pulley D is given as 0.6. So that is our coefficient in this case. Now to determine the angle beta here, what I'm going to do is, so for this one, since what we know is this angle this side, this is 60, instead of the 60, I'll select 60 from 90 degrees, and I am going to find this angle this side as 30. Then I'll subtract 30 from 180 to get the angle that we are looking for, which is the angle of belt surface contact. So that's going to be the angle from here all the way up to here. So if we do the math here, when we subtract 30 from 180, we get beta as 150 degrees. So beta here is going to be 150 degrees, but we need it in radians. So we're just going to say 150, multiply this by pi over 180. So of course we just simplify this. We get 5 over 6 pi as the wedge, as the angle of belt surface contact. Okay, this now is in radians. So I can now just plug these two values, these values there, and see what TDE will be. So we get TDE as, let's see what we have. So where there is mu, we'll put what the coefficient there is. That's 0.6, that's 63. Was it 63? Let's see. Yeah, that's 63. And then the angle there, so we're using 5.6 pi radians. So I hope you saw how I got that angle. Since my angle was given as this one here, and my pulley is turning in this way, so what I did was I used this one here instead. So I lessed this from 90 to get the 30 here, and then I lessed 30 from 180 to get what my surface angle here was, because it's like the 30 that is there is basically yeah, what completes, I think, yeah, it's like we have something up to something like this. Let me draw it like this. We have this, and then we have that. So this is where that beta is. So the 30 is what actually gets to complete this when you do that. So the 30 would be somewhere here. Okay, so if it were that our pulley was coming out in this way, then of course we'd have to use the same 60 here. Okay, so let's do the math here. What are we going to get? We get TDE. So this comes out as 4790.754721 kilonewtons. So this is the force between the force acting in that rope after the tension D, after the pulley D. After doing that, we observe that that tension will be the same even here, since this is free to rotate. So we'll just bypass that one. Now what happens? Now we have to do the same math, but now just at this pulley. Now what happens here? Of course, for this one, the angle of contact, you have to see that the angle of contact here, you can guess what this is going to be. So here the angle of contact is just going to be 90 degrees. So let's see how we're going to do the math. We're given what the coefficient for that pulley is. That's pulley E. So the coefficient there, mu, where is that? Between, where is that? The rope. Between the rope and pulley at E, that's 0.49. Okay, so the angle there we're using 90 degrees, which is pi over 2. So in that case again, the tension now we're looking for, or if I was to draw a free body diagram for that one, this is what we have here. Now we have this tension here, which is TBE. Is that E down there? That's F, sorry. That's EF. So TEF. Now this side, we have the one that the cars are exerting, which is T. So this has to be greater again, so it's the one that takes center stage. So it has to be TEF, and then you have E, and then this side you're going to have the coefficient for that pulley, then multiplying again the angle of contact. In this case, the angle of contact is pi over 2. So how does it work? So again, we already have what the force is. So just get the force and plug it there. And we did get the coefficient, but I think it's way gone from my calculator. I have to get it from my clip. Let's get it back. So here the coefficient is between the rope and E. It's not E we're going for, that it's F instead. So let's see what this is. I'm not sure what this is. It looks like 0.83. So that's 0.83. Let's take it as 0.83. Okay, so if that is 0.83, then that's what we use. Okay, so let's have 0.83, and then multiplying the angle in radians again, so that's pi over 2. So if we do the math here, T comes out as, okay, so we get this value. So I hope you guys saw that we have a decimal here. I don't know why I didn't write it there, but we have a decimal there. So this is what we get as the actual tension that was exerted by the cars on the rope. Now guys, share and like the video if you found it helpful. If you have any reaction, please let me see them in the comment section. And yeah, again, when we exceed let's say 50 likes, I'm going to make a video for the next part. Bye guys, see you in the next one.